I'm standing in for Ziv today, who's gone home for the holidays, but it gives me great pleasure to introduce Mattias Juhl to you all today. Now, you probably know Mattias as a champion high jumper. He was awarded at Marsland High School more than 10 years ago, I imagine now. But also, Mattias is one of our undergraduate PV program students, and he's been in the photovoltaics industry now for more than 10 years. Now, I met Mattias when I was tutoring a course. I think it was solar cells. He was one of the students in there. I was a substitute tutor, and along with Ned, who just walked in, and probably a few other people. But Mattias and Ned were those terrifying students that you have when you're a tutor that asked questions that you were completely unprepared for, and you knew were really good questions. So it gives me great pleasure that Mattias continued on to do a PhD with us here at UNSW, and today he's going to tell us a bit about the results of his PhD work, which he did with Torsten and Martin. So I hope you'll all join me in welcoming Mattias to this week's seminar. Thank you, Mattias.
Thank you, Craig. That was a very nice introduction, Craig. Thank you very much. So I'm going to be talking about what I did in my PhD, and I've been able to summarize it well enough that we shouldn't be here too long, I don't think. So my PhD was on the application of the spectral response of photoluminescence in photovoltaics. And of course I was a student, and my supervisors were Torsten Trupke and Martin Green. So I had a very strong panel of supervisors there. So it's a big title, there's a lot of words in it. I'll just go through and make sure we all know what they mean. So photoluminescence is basically radiation that comes from a sample that's not related to its temperature. And specifically here, what I'm going to be talking about is luminescence that comes from radiative recombination of an electron hole pair. So photoluminescence is, of course, a type of luminescence. And it's where the electron hole pairs have been generated by incoming light. So what we do is we get some light, we shine it on a cell, and then look at the light that comes off it. Pretty simple. And you might ask, why photoluminescence? Well, I think it's a great characterization technique. It's contactless, it's fast, it's been able to already determine a myriad of parameters for solar cells and other semiconductor devices. Surface recombination, lifetime, diffusion length, doping, and the list goes on. But what am I measuring? There's a few different ways you can measure photoluminescence and a few different characterization methods about it. How I'm doing it is very similar to photoluminescence imaging, a technique that was pioneered by my supervisor, Torsten Trupke, and is now spun off into a company. Instead of, what we do is we basically get a silicon diode or a silicon camera and measure the radiation that leaves a solar cell or wafer, and we don't have it contain any spectral information. We just, for every one point or one sample, we get one number out. So this is very different from, say, spectral photoluminescence measurements, which most people I find not in PV are more familiar with. So, as I said, this technique has been around for a long time. It's been applied from bricks to modules and determine almost everything else you can get from a solar cell. So what am I doing that's new? Well, that was the rest of my title, the spectral response. So the spectral response is basically, we're going to look at different parts or different illumination wavelengths and see how properties vary. You will all know the most common technique used in photovoltaics, spectral response technique, which is the EQE, and the definition is just in the bottom right-hand corner there, and it's just short circuit current over Q times incident photon flux. And it's just a particle conversion, the number of photons in to the number of electrons out. And here we have an example measurement. And on the left axis we have EQE, and on the bottom axis we have wavelengths. And of course, we have a good measurement here to start with. We have a high EQE, so a high conversion of light to charge. And as we go out to longer wavelengths, our cell can't really absorb anything anymore, so it falls off. But there are many things that deviate from this, and we can see with an EQE measurement. A blue dead layer or some absorbing structure at the front surface recombination in your cell, poor bulk lifetime, there's a dip in the back, and very similar as the rear surface recombination, and finally light trapping. So hopefully you'll agree with me that there's a lot of information there. And to date we haven't really gone too much into photoluminescence. Of course, photoluminescence been around time, so I have to caveat that there actually has been some work done in here. And it's done using spectral photoluminescence measurements. So Rao and Kierkegaard's, they went through and said, if we get the spectral photoluminescence measurement, we can actually emulate these curves brilliantly. But unfortunately, silicon only luminesces at wavelengths longer than 900 nanometers. So you're only getting a third of this kind of information, wavelength information here. So I thought, well, let's change the illumination wavelength and see what we can get out. And so with a proposal like this, I went over to our previous head of school, Richard, who was head of school at the time, of course, and Martin, and they were kind enough to give me a bit of money and modify some equipment and see what we could get out. So I've got two applications that I'm going to be presenting that we investigated. The first one is obviously into band-to-band absorptance. The absorptance of a solar cell is just how much light goes into how much doesn't come out. So what's absorbed in it, basically. The band-to-band part tells us the process that's going on. So band-to-band here we mean any optical process that will result in a free carrier or electron hole pair generation. So the process we really care about in solar cells, generating electron hole pairs. And the subtlety around that should become clear on the next slide. If it doesn't, let me know. We can clear it up here. So we need a relationship between photoluminescence intensity and absorptance. It'll just take one slide. It's pretty easy. The photoluminescence intensity can be found from the Van Rosebeck formula as the product of the carrier densities. So in low injection, we have the PL intensity, top left, is proportional to the minority carrier density times the bulk doping. And then if we rely on our old lifetime equation that says a minority carrier lifetime is equal to the excess carrier density over the generation rate of electron holes, we could put those together and we can see that the PL intensity is going to be the generation rate times this effective lifetime value. Now, if we assume a constant lifetime, we can get the PL intensity is proportional to the generation rate of electron and holes, which of course is the band-to-band absorptance times the incident photon flux. So we have a value proportional to the band-to-band absorptance. Wasn't so hard. PL intensity divided by the incident photon flux. Now, we have a structure here that we can follow, and now we can investigate something. So of course, we have to build a tool. I'm just going to throw that formula in the left-hand side, down the bottom corner there, you can look at if you forget it. Here's the tool we went and put together. We'll start up the top. We've got a couple of different lasers there. One at 1060 nanometers, the other one at 808 nanometers. They're our illumination sources. They're the wavelengths we're going to be investigating. So they produce light, shown by the blue lines, that comes down onto the sample in the bottom in green. The sample absorbs the light and then emits it again as photoluminescence, indicated in red, which will be detected by the camera. So one of the things about, so at 808 nanometers, a sample pretty much absorbs all the light. While at 1060, we know that a lot of the light can pass through a sample. So to make sure we're not impacted by the stage, we had a stage where we had a big air gap at the bottom. So light could pass out of the sample unhindered. And by doing this, we could compare our measurements we did this to standard optical techniques, such as reflection and transmission. There's one little thing I just want to point out. This is a side note. I just like this. So if we look at the spectrum of where we're doing things, on the left, the new figure that's appeared, in green we have the laser that's 808 nanometers, so there's the excitation. The other laser is shown in red in 1060 nanometers. The blue line shows roughly the PL emissions according to Planck's law. And the detector that we're using is a silicon detector. So we can't detect anything longer really than the 1060 nanometer illumination. So actually detecting at shorter wavelengths, which means higher energies when we're using the 1060 nanometer laser. So we're actually detecting thermally upconverted photons. So I thought that was pretty cool. But that's just a side note. So we had the system. we can measure 2 different illumination wavelengths, and then we can check out how the absorptance goes, but we needed some samples. So we went for the easy case first, some well-passivated samples with different optics. So we grabbed some planar samples and thinned them down to different thicknesses, and then we also textured some. We also made a couple of cells to put in a bit of free carrier absorption in there, because that's not band-to-band absorptance. And then we compared our measurements we did to optical measurements and EQE measurements. So the optical measurements of reflection and transmission measurements. So on the left-hand axis here, we have some strange metric, which is the absorption ratio at 2 different wavelengths, and that's determined from photoluminescence. And on the x-axis, we have the same absorption ratio determined from optical and EQE measurements. So this strange ratio down the bottom, it's quite simple. Because our technique is a relative technique, the absorptance we're measuring, if we see in the left-hand corner, is proportional to the photoluminescence intensity divided by the photon flux. But if we now measure that for 2 wavelengths and divide them, we get an absolute value. So we can compare an absolute value to something, to other techniques. So that's what we've done in this ratio, the equation on the bottom right-hand side. We divide the value we get at 1060, the absorptance value, by the value at 808, and we get an absolute value which we can compare with the other techniques. And you can see it looks like quite a good agreement for quite a wide range, from 20 up to 80. And you can imagine we're only here going between possible values between 0 and 100. So it was quite good. We're quite happy with that. But I know you're thinking, didn't we have a camera involved? We did. So we did imaging too. So this is a multicrystalline sample, no diffusion or anything. We threw it into an alkaline texture, which means we get random pyramids being generated everywhere. But because it's multicrystalline, they're all generated in different directions. So each grain has different light trapping properties. So we're hopefully going to see some variation across the wafer. On the left there, we have the PL image with 808 nanometers, and on the right, we have 1060 nanometer illumination. We can see a lot of structure in there, some differences between the two, but these differences really become more clear when we calculate that absorptance image. So now we're just doing that same analysis as before, but on a pixel by pixel level. So the immediate thing you can see is the disappearance of structure, those fine structures that are happening. And I'd like to bring your attention just to 3 points in this. We can hopefully see it a bit better. The first one in the circle, in the 808 nanometer image on the left there, we have a defect cluster or a grain boundary. And on the right, the absorptance image, it's almost completely disappeared. And that's because the lifetime features are present in both images and are really cancelling out quite well. Now, if we look at the absorptance ratio image, we can see grain A and B. They have quite a different absorptance ratios there, with B showing much stronger absorptance at 1060 relative to its 808 than grain A. While in figure A, you wouldn't be able to discern this information. And in fact, it hints at, because grain A is actually brighter in the 808 nanometer image, but it has worse light trapping properties, as we can see in the 1060 nanometer image, it hints that grain A actually is a better lifetime grain. So again, we're quite happy with the results, but you need to quantify it to make it believable. So we went and did that as well. We got the sample, we threw it in a Perkin-Elmer, we individually analysed the absorptance of each grain using a transflectance measurement, and we plotted them here. So again, quite good agreement. Really quite happy there. And that really brings me to the end of my application number 1. We move on to, oh yeah, it works. Application number 2, the external quantum efficiency. So we saw earlier that external quantum efficiency is often used in photovoltaics, and now we're trying to replicate that in a short wavelength range. So again, we need some relationship to relate PL to external quantum efficiency. It turns out not to be so hard either. The standard definition that we saw of external quantum efficiency earlier. Now, if we think of the one diode equation, we can easily see that short circuit current is proportional to the exponent of the voltage on VT, the left-hand side there. We lose the proportionality because there's terms like J0 and Ni in there. That's fine. We're not so worried. Proportional's fine for us. Now, on the right-hand side, we have the photoluminescence intensity, and you can find that through Planck's law, that the photoluminescence intensity is proportional to the implied voltage. So if we say the implied voltage is equal to the terminal voltage or the open circuit voltage, then, and low injection, we can say that the EQE is just proportional to the photoluminescence intensity over the incident photon flux. Fantastic. We now have another form that we can play with and analyze. All right, so I'll again put that in the bottom right-hand corner, just if you forget it. And so we, of course, went through and decided to make an experimental setup. We got a bunch of high-powered LEDs. Then when you turned them on, we made it hit a beam splitter, split off it, measure the reference intensity with another photodiode, while the rest of the beam would continue through, hit the sample would absorb the photons, and emit from the other side where we'd be detecting the photoluminescence. So a classic transmission photoluminescence detection setup. Of course, we hooked some preamps in there to get a bit of sensitivity and all connected to a computer. Lovely, we've got a setup. All we had to do was change the wavelength was to switch over the high power LEDs. Too easy. And so these are the LEDs we went with. We went for the short wavelength range for two reasons. One, we saw before that hasn't been investigated with photoluminescence yet, but also we have photoluminescence being emitted at longer than 900 nanometers. So we can't really detect and illuminate in the same range. The optical filtering becomes quite hard. So we got this set up and we had to test something. The thing would start off, we thought we'd start off with testing, is up the top. We did a split based on different silicon nitrides. We had the standard one and one we knew that was more absorbing. And so of course we're going to measure EQE, so we needed cells in there, which is on the bottom left-hand side. And above that, we couldn't actually measure the cells on our photoluminescence tool because it was a transmission measurement, and we were making standard screen print cells at the time. So we had to make lifetime structures, which is just a symmetric structure. So in the blue we have P-type wafers, and you'll see that they've got an N-type diffusion on all their sides, very standard process. We then covered them with silicon nitride, and then metallized the cells. We made sure that the lifetime structures went through all the same thermal processing as the cells. We then sent the lifetime structures off to an EQE measurement, EQE-PL measurement, and the cells off to a standard EQE measurement. And we got some good results. So in the full lines, we have that standard EQE measurement that everyone should be quite used to. And you'll notice that there's a split between the two different silicon nitrides. The standard silicon nitride that we were using was in yellow, and the one with a more absorbing recipe was in blue. And so you can see that change in the short wavelength there. The EQE-PL measurement, or the measurement done with PL, we can see in dots for those discrete LEDs that we had. And we're seeing quite a good match here for the shapes. Now, of course, this EQE from PL is a relative technique. So these values are scaled vertically to match the standard EQE technique. But again, the same shape is seen in both the EQE, the standard EQE technique, and the one that we've done with PL. So again, we were quite happy with this. It works. So conclusions for the applications. Looks like we can determine the band-to-band absorptance, and we did it with imaging, as well as external quantum efficiency. I mean, you'd all be pretty comfortable with that, wouldn't you? Yeah. I know what you're thinking though. Not quite. We all noticed that, didn't we? That the EQE at 800, they didn't really match. You know, this guy? Yeah, we noticed him too. But it didn't turn out to be so bad. This opened a little extra area when I went looking around with, and it turns out that I wasn't the first person to run into this bit of deviation. There was a guy from ANU, Helmut Mackel, who did similar work, but with excess photoconductance rather than photoluminescence. And he got the deviations too. And he could measure further into longer wavelengths and showed there were bigger deviations. But he never really focused on what they were coming from. He more pointed out that they were there and suggested a few causes. So I think I took off where he left off. And I'm going to be saying, hopefully, by the end, and you'll agree with me, that they're caused by voltage-independent carriers. Now, I know what you're all thinking, voltage-independent what? Mattias has made up a strange name. But no, it wasn't me. I didn't make up the name. It was a guy called Glather. And I've stolen the terminology from him. And the terminology is basically two terms. We've got a voltage-dependent carrier and a voltage-independent carrier. So what that means is we have one set of carriers that depends explicitly on the junction voltage and one that doesn't depend on it at all. We're going to try and use a bit of a graphical demonstration here to give you an idea what I talk about. So these are simulations done in PC1D. On the left axis we have the minority carrier density. On the y-axis we have the minority carrier density, and on the x-axis we have depth into the wafer. So in that blue line is a cell that's forward biased up to a terminal voltage of 624 millivolts. So these carriers are only there because we're applying a voltage. So they have to be voltage dependent. Now, if we illuminate with a longer wavelength, here 1100 nanometers, and we take away all bias, so it's an open circuit, and we match the photon flux so we get the same terminal voltage, that's 624 nanometers. And we can see that because at the front of the cell we have the same carrier density. But into the depth we have a different carrier density. So if we have a voltage dependent part and a voltage independent part, everything that's not voltage dependent must be voltage independent. And we can do this with another wavelength, say 950 nanometers. We get a different excess carrier density, but we've got the same terminal voltage still. So again, we have that voltage dependent part and that voltage independent part. And now you can do this with even shorter wavelengths. So all the generation is in the emitter. And we did that too, 300 nanometers. So there's no generation in the bulk. And then we get one carrier density, and that's the voltage dependent part. Now this is a very hand-wavy argument, but this is really just to get you in the mindset. Hopefully I'll be able to convince you that there really is a voltage dependent part soon, and voltage independent. And of course, to do that, we're going to go back to a bit of maths. Where else to start with in solar cells but the continuity equation? We've got a drift term, some recombination and generation, very standard. And we're just going to pull out the general solution, constants with depth, and then at the end term we have there a function of the illumination wavelength. Now, it's an inhomogeneous differential equation, so we know superposition holds. So what we're going to try and do is say there's a voltage-dependent term and a voltage-independent term. Now, I'm not going to take you through all this, but basically all you need to assume is you fix a carrier density at one side of the cell, we call that a voltage, and at the back you let it fluctuate, however you want. And there are your two boundary conditions, so you can solve this whole system. You put that through and you get these two terms. You really do get a voltage-dependent term and a voltage-independent term. Here, the voltage-dependent term has two components. These material constants with this depth factor that's in the general solution, and this term at the end. Everything's multiplied by a voltage term. So it's voltage-dependent. The second part is voltage-independent. And again, we have this term circled in blue, which are just dependent on material properties. And at the end here, we have a factor that relies on illumination wavelengths and the number of incident photons. So we really have a term that is solely dependent on voltage and one that isn't dependent on voltage at all, but is dependent on our illumination. So this is where the terminology can really stem from. Now, I know a lot of people don't like maths explanations, so we'll do it with graphs as well. So in the top left corner, we have that same simulation set we saw before, with a terminal voltage with 624 millivolts and a bunch of different wavelengths. Here, it's actually a bit easier to see that 300 nanometer illumination. The 300 nanometer illumination is in orange here, and the dark case is in a dashed line, so it's a bit easier. Sorry about that before. On the right side now, we're going to do those exact same simulations, but short circuit the cell. Set the terminal voltage, set the junction voltage to 0. So we can see that at the front of the cell, all the carriers have dropped down to 0. We don't have any there, but we still have carriers remaining in the bulk. Now, what we're going to do is we're going to put these together. We're going to invoke the rule of superposition. So the full lines in C down the bottom are the same as the simulations up in A, the open circuit simulations. They're the same data, the full lines. The dots is the sum of the carriers in B plus the excess carrier density you get just by applying the terminal voltage, so the dashed line in A. And you can see really good agreement. And all it's really showing is these carriers, that are voltage independent, so the carriers up in B, are not changing in location or magnitude as we sweep the terminal voltage from open circuit to short circuit. They're not moving. They really are voltage dependent and voltage independent. But why do we care about them? Because they do cause problems. And that is, if you ever try to do implied voltage from a lifetime, they can cause a problem. They can cause a deviation. If you ever do lifetime from an applied voltage, or lifetime from a real voltage, they can cause a problem there. And of course, they can cause a problem if you're measuring the absorptance from the average excess carry density like I was earlier, which is one of the reasons we started with low surface recombination velocities. Now, down the bottom, we've already seen this figure from Mackle before, how we had that deviation at long wavelengths. Another example in published literature was a paper out from UNSW by Malcolm Abbott, who's still here, or who has come back to us now. So this is a comparison between a very standard measurement, SUNS VOC, which we see in the black dashed line, as well as SUNS PL. The difference between the two is SUNS PL, we just calculate an implied voltage from the excess carry density. And you can see there's great agreement between the blue line and the black dashed lines for high voltages. But as we're going down to lower voltages, we're getting this big difference coming out. And that's because the terminal voltage was really being pulled down. So the voltage-dependent carriers were being pulled down quickly, while the voltage-independent carriers were remaining. So you end up with a measurement of those. Now Malcolm suggested a correction, which was basically subtract a value proportional to the generation rate. And as we saw before, the voltage-independent carriers are proportional to the generation rate. And that correction is shown in the red dotted line. And you can see great agreement between the SUNS VOC and the SUNS PL with that correction term. So they are real, and they do cause problems, but we can correct for them. So when do we need to worry about them? The answer is always it's complicated, but we'll see if we can make it a bit simpler. It all depends on this product and what we're trying to measure. So we have the total carrier density as a function of voltage-dependent terms and voltage-independent terms. And it's just that balance between them. Now, if we were doing an implied measurement, applied voltage measurement, if our excess carrier density was always only measured the voltage-independent terms, then it would be correct, because you always have a signal that's related to the voltage. So that's fine. So really, what we have to consider is, how do the voltage-independent carriers behave? And is there some point where we can just ignore them, or are they constant or something? So I went through and had a look at that. On the x-axis, we have the bulk lifetime, ranging from tiny values, 0.1 microsecond, all the way up to hundreds of microseconds. It's quite big. And on the y-axis, we have the average, the integral with depth of voltage-independent carriers. And we've also got plotted here very different rear surface recombination velocities, from 0, so perfectly passivated, to terribly unpassivated, 1e7 centimeters per second. And it's the same general trend for all these simulations. I should say these simulations were done at 1,000 nanometers, but they're general for, you can do them at any wavelength, and they're true. We can see as soon as you start to get to 100 microseconds in lifetime, we get this plateau. And that's bulk lifetime, not effective. So for standard CZ material, we're usually looking at samples in that range. So so we can start from there and say, well, then we have a plateau, so we can quantify how much our voltage-independent carriers really are for standard material. And if we want to make sure we're not affected by it, times that number by the 100, divide by the generation, and we have an effective lifetime that we don't have to worry about them for. It's pretty simple. And so we did that calculation for, because it's wavelength dependent, of course, we did that calculation for all the wavelengths as a upper limit when we don't have to worry about being affected by voltage-dependent carriers anymore. And you can see at short wavelengths, you really have, we're talking about the figure on the left at the moment, we really don't have much to worry about. For effective lifetimes over a microsecond, it's quite hard to get that low. But for longer illumination wavelengths, where the generation rate is more uniform, we're talking about effective lifetimes over 200 microseconds. It's quite high. Now, you can also talk about this same thing in terms of your uncertainty in the implied voltage that you're calculating. And of course, you can change effective lifetime into voltage. And we've done that for the right-hand side here. So it's just, what effective lifetime do you need to make sure you have less than a 1% deviation between your actual voltage and your implied voltage. And you can see the lifetime curve is just shifting down a little bit, but it's the same general trends. Now, you'll notice, being a very intelligent room, that the short wavelengths, there's a bit of difference between the two. There's a plateau in the one on the left and a dip in the one on the right. But this is just because of the different ways that they're calculated. The one on the left is calculated from simulations in PC1D, so there's an emitter. And that plateau is actually related to the emitter having diffusion, voltage-independent carriers in them. While on the right, it's done from analytical solution assuming no emitter. So that's that small difference. So we just seen that these carriers do matter, they can affect us, and we've got a rough idea of when they do. And they're really bad at long wavelengths. And that's what we're exactly seeing before with that small deviation, really emphasized by Mackel's work. So, yeah, sorted. And it brings me to the end of my quick talk. The conclusions are we were able to demonstrate we can measure the band-to-band absorptance on solar cells using photoluminescence. And if we get a sample with no voltage-independent carriers, we can measure EQE accurately over any wavelength range. And the carrier density can be described in terms of these two components, voltage-dependent, voltage-independent carriers. And just to note that the conversion from lifetime to voltage doesn't always work, but we're usually fine. Thank you.
Any questions from Mattias?
Dave.
So your PL EQE at the moment with your LED system is just at like 4 wavelengths or something. Are you working on, or have you got a system that can scan like finer wavelength detail?
No. That work's being extended by a new PhD student here, but same kind of discrete LED-based system, just more wavelengths. Thanks. Hannah?
Very nice presentation, thank you. Question, if you have done, or if you have created already the link between lifetime and injection independent carriers, can't you just measure the lifetime by just measuring the independent carriers?
Yes, you can. The real problem is, so this hump here is, well, you need to know two things. You need to know the real EQE or the real absorptance to be able to figure out how many independent carriers there are. And with EQE, you know that you can't really measure surface recombination velocities when they're getting below 1,000. It becomes really tricky. And it's roughly the same for these values, for this big hump. This hump is really apparent when you have a bad front surface because it brings down your voltage-dependent carriers. So you can do it, but I think the usefulness for PV in investigating these areas becomes quite hard because we're already to such low surface recombination velocities, with like standard screen print rears being a couple of hundred.
But you could even enhance this by putting the junction voltage to 0, right? Like you just short circuit the cell, then you know, okay, you have 0 carriers at the junction. Then
Yes.
you only have the independent carriers. And if you have a cell already in line, you know the current and then you can like calculate back.
But so this is roughly what you'll be getting out.
Yeah.
So if you have bulk lifetimes over a couple of hundred, you won't really be getting out any information. If you have surface recombinations between 200 and 0, or 100 and 0, you're looking at a very small value you're going to be trying to calculate. So you can do it, but I'd question the effort involved for the reward. Thank you. Yeah. Thank you, Omar.
Well, if there are no further questions, I think we should thank Mattias for a wonderful presentation.
I have one more question.
Oh, look. Oh. Sorry, we clapped.
So how high did you used to jump?
It was a sports carnival, I think in year 8, where I got a gold ribbon or something. Craig was just asking me for... Oh, I think I was taller than every other kid in there. Yeah.